station today from Energy Expected.
Right, so welcome to today's tutorial. Today's tutorial is mainly we're going to talk about batteries again. So what prompted me to do this one is the realization that we seem to have a challenge with regards to batteries. There are a lot of failures, or rather battery failures, around the world. So a closer look at the failures is suggesting that there is need to educate the end user more on how they should actually deploy their batteries, or how to choose their batteries. So to do that, we are going to do about 3 or 4 tutorials that is going to be focused on batteries. So we are going to be talking about the materials in manufacturing design process of a battery. This one is mainly the chemistry behind and the materials that are used and how they affect battery life, battery performance, and then we are going to talk about the external environment to the battery and how it affects the battery life and battery performance. We are going to talk about the charging methods and how they affect, or rather charging and discharging, and how it affects the battery performance and battery life. Then we are just going to generalize everything and then summarize. So what is a battery, right, really? So a battery is a storage facility which stores electrical power in the form of chemical energy. So what we have in the battery is chemicals which later on reacts spontaneously to give out electrical energy, right? So the design and the manufacturing process is involves the chemistry, material science specialists, and the electronics specialists. The chemistry part is the heart of the battery. It is like where everything starts, right? So these guys come and then they determine the quantities of the reactants that we call the active material within a battery. What is these materials? We have positive and negative electrodes. We have got an electrolyte. We have things like the separator, which separates the negative plate and the positive plate. So the chemical or the chemistry guys determines how much those quantities are going to be mixed in order to give a specific battery capacity and a specific life of that battery. It is determined or derived from the active material that is within the battery that is going to be put in the battery, right? So after that process, after the process of determining the ratios, the quantities of the active materials, the plates, the grid, well, after all that is done, and when the battery is finally sealed, everything is done, the pressure test on the container is done, and all the electronic simulations to determine the lifespan and performance is done. The client comes and is supposed to buy the battery. Now, the uses of these batteries differ, right? You can buy a battery to use as a starting battery on a car. You can buy a battery for use in heavy mining equipment. You can buy a battery to use on lawnmowers. You can buy a battery to use on backup systems, which is our main focus in this case. But still, whilst we are looking at the backup systems, we find that we have got quite a range of appliances within within our houses, within our offices, and within where we would want to have backup or battery backup power. The nature of these loads should make one choose the right battery, so that it's not going to be strained when it is being used, so that it's not going to be underutilized, so that one realizes their value for money. So I talked about the active material inside the battery, right? I'll give you an example of how a design can change where a battery is supposed to be used or deployed. You can have a plate that is thin and very big, with a very big cross-sectional area. What it simply means is this plate is providing a very big surface area for contact and reaction between electrolyte and the paste material on the grid of the plate. So, but because it's thin, it's not going to last long. Like if it is going to be giving out electrons, it's going to give lots of them, but not for a big duration, because the plate is thin. Whereas you can have a plate that is thick. What it means is this plate is going to give out electrons that are then forming the current that you want. It's going to give that the electrons for a bigger duration of time, because it's thick, you see. So when the batteries are designed, it is very, or rather when one is choosing a battery, it is very important to know where exactly you want to use the battery and which type of loads are inside your house. Are you going to be using the batteries to run a pump? What size of the pump? Is this pump connected through a soft starter, or is going to just run like without a soft start? Is it going to be like are you going to supply the battery are you going to use the battery to power television sets or NX saver lights or refrigerators and so on? So it will help when you go to the shop, you then check the specification on the battery. You see that, okay, this battery is 200 ah, and the rating is C20 or C10. Okay, so what is the rating? Let me just talk about the rating. So the rating is the C, or rather the C rate, the C rating of the battery. This is the time that it will take when it is discharging a certain amount of current. This is the design rate that is safe. For example, if you see a battery return C10, it means it will give 10 hours discharging a current of 10 into the ampere hours that are given on that battery. If it is a 100 ah battery, it means it will safely discharge 10 amps for 10 hours. If it is C20, it means it will safely discharge 20 into 100 current amps. So if you exceed that, what you are simply doing is you are forcing the active material to overreact so as to give you the amount of power that you are demanding from the battery. Now, what is going to happen inside the battery is there is going to be a lot of heat production. There's going to be physical damage to the plate material and that paste, and there's going to be deformations. There's going to be a lot of things that is going to happen, such that when you want now to reverse that reaction, sometimes it will then fail. Maybe one cell would have completely collapsed, such that in a 12 volt nominal battery, you will then never get 12. You will be somewhere around 10 or 9 point something, because you would have completely damaged one cell. So unfortunately, for maintenance free batteries, nothing would be possible. It will be like a write-off. You have to take it back to the manufacturing companies, where they will have to destroy it and extract lead for reuse in other batteries. They won't use that exact battery, but they will have to destroy it and use electrolysis to get the lead for use in other batteries. So what is the other thing that we talked about, or we say we're going to talk about? When you now know that you've got a fridge that you want to use, the nature of load you now know, then the next thing is to read the specification of the battery. There is what is called the depth of discharge. So battery life is given in number of cycles. So number of cycles, a cycle is a charge and a discharge. Charge and discharge. So the depth of discharge affects the number of cycles, or affects the battery life in a very funny way. It's not linear. So most of the batteries, they give a longer life, like 4 years, if you are discharging 20% only. If you are taking 20% of the power from the battery, then you know that you may take 3 to 4 years with your battery, the gel batteries. There's a lot of misconception that the gel batteries are not strong and so forth. No, that's not true. It is about how we use them or how we deploy them. If you take 50% from that battery, it will reduce the life possibly by half. So um, when where you were supposed to get 3 years, when taking 80%, 20% of the power, if you are getting 50%, you may reduce the life from 3 years to 1.5 or even to 1 year. If you go further to take 80%, you can even get 6 months. Then the battery is gone. Not that it's dead or is damaged, no, but the active material has been used up. There's nothing that can react to give you power. You can't reverse the reaction, nothing. So the battery is used up. We have to take it back to the manufacturing plants, at least because they can reuse some of the active materials that are inside. So then the other thing is charging. We talked about discharging, right? That you are supposed to discharge 20% or at most 50%. Beyond that, you know that you are playing in the dangerous zones. Your battery is not going to last. So charging, a battery is very sensitive to charging, right? We talked about a separator that is inside the battery that separates the negative and positive plates. That separator is sensitive to temperature and it can disintegrate at some temperatures. Like if the temperature is above 60 degrees, you know that for flooded or gel batteries, you know that the separator is at risk of disintegrating or collapsing, and if it collapses, then there is going to be an internal short circuit between that negative and positive plate. Then it can be an unfortunate event, it can be an explosion. So charging has to be controlled. Charging is controlled through deployment of charge controllers and with the help of battery management system as well. So the battery management system is a system or is a monitoring system that monitors parameters within a battery, like temperature, like electrolyte level, specific gravity, voltage, So when these when one of these is about to go outside, then at least you get a signal to say this one temperature is high. A charge controller can then cut the charging, right? So charging is very important. A battery should not be overcharged and a battery should not be undercharged. If it is undercharged, then there are some compounds that will form. There's what is called sulfation that will happen, and unfortunately this is like a subtraction of the active material that gives us a capacity. So if sulfation occurs, it's like you're subtracting active material that is supposed to be working to give you power, or it's the storage capacity that is being subtracted. So if it happens such that you can't reverse it, then you know that a 100 Ah battery would have deteriorated, say, maybe to 90 Ah battery. What you will be reading is you will be reading like I have got a 100 Ah battery on the nameplate, but inside the battery the active material is no longer sufficient to store 100 Ah or equivalent of energy. So that is as a result of undercharging. So how do you avoid that? So that is now a question of balancing the amount of energy source, the connected load, and the storage. Whatever source of energy is bringing power to the batteries and to the load should be sufficient to charge the batteries to full and to supply the connected load. So that has to balance. Otherwise, if it's such that the source is smaller than the two, then the battery is going to be starved. And as it continues to get starved, it continuously deteriorating capacity slowly, and then you don't have capacity. It's like a scenario where you charge a battery. Within 30 minutes, it's telling you that the battery is full. But when you try to then connect a load or discharge it, in the first 20 minutes, it's already giving an alarm of battery empty. You see. So I thought that maybe these highlights of what exactly is a battery and how it should be managed can help someone today. So for today, I will end here. I will continue again to talk about batteries, trying to give practical examples of where I've seen batteries failing and what was the cause, and things like that. So I thank you for today. Please subscribe to our channels for more videos, and also please ask questions. Let's engage, leave questions so that we can address the questions, and then we can grow together. Thank you very much. Thank you.
Book a free consultation today from Energy Expert.